Hello students, welcome to this lecture. And in this particular lecture, and then going forward in the lecture series, we will do an in-depth analysis of the power for a circuits and the energy for the circuits, especially for the digital circuits, right? Because anyways, we are looking into the digital component in this particular course. So let's begin further. Let's move further. So let me take my pointer as well. So as per the definition for the energy consumed by a particular component or by a particular circuit, it is defined as nothing but the power, instantaneous power that has been consumed by the component, or it has been dissipated by the component over a period of time, right? Over a duration of time. So it is basically an integral component. So it is defined the energy that is consumed by the power or dissipated by the consumed by the component or the dissipated by the component is actually defined as an integral of the instantaneous power across the time duration. So what it really means is, if I have a discrete point of time, then it's nothing but the summation of all the power across the time duration. So that's why, in a very analogous term, we will consider it to be nothing but an integral component. And instantaneous power is actually defined in the form of the product of the voltage across the component at that particular time instant multiplied by the current flowing along the component for that particular time instance. Right. So if this is the energy that has been defined, or this is the energy that has been estimated for the component or for the circuit that has been designed by us over a time duration of t, then I can also estimate what is the overall average power for, if this is particular energy for a duration of 0 to t. So that particular power, the average power across the time domain of 0 to t can be given as nothing but the energy divided by the time duration t. So in that sense, it is nothing but the average power turns out to be nothing but 1 by t, and then the energy definition, which is nothing but the integral of 0 to t, and then the instantaneous power of dt. Right, so remember that this P of t is an instantaneous power, that is nothing but the power released or dissipated or consumed at that particular time instant, and P average is nothing but whatever is the average power across this time duration of 0 to t. Right, so if I have the instantaneous power as something like this, then so this is my P of t across the time domain t. Then I will have an average power, right, which is nothing but an average of across all these points. So I will have somewhere like this. So this might be my average power, right? So that is consumed or dissipated or released by that particular component over the time duration from 0 to t. Right, hope this particular first level definition of the power and energy is is clear to everyone. Going forward, so now let's try to apply or extract the power parameters and then the energy parameters, right, for our digital circuits. And the most primitive digital circuit turns out to be the inverter. So I have designed an inverter here with an input here and then a capacitance. It could be a parasitics, or it could be an input capacitance coming from the next stage. So we can consider this to be nothing but a C value, which is nothing but a load capacitance connected at the output node. Now I've drawn this particular an arrow showing that the capacitor is actually charging through the PMOS transistor, and we'll say that okay, the NMOS will be off, considering the input is nothing but a step input, right? So 1 to 0, then I will have the PMOS to be on, NMOS to be off. If I have the 1 to 0, or rather 0 to 1, I will have the NMOS to be on and PMOS to be off, and then the capacitor will be discharging. So for the capacitor to charge, we will try to evaluate what is the energy that is being consumed by the capacitor, right, while it is actually charging. right? And while it is charging, we know that for a step input, we will have the PMOS to be on and NMOS to be off, and thereby I will have the current going from VDD and then through the PMOS and then charging the capacitance. So as per the definition, the energy consumed by the capacitor or by the component, in this case the capacitor is the component we are interested in, is nothing but for t is equal to 0 to infinite. So I've taken the t is equal to infinite because we really don't know at what time the capacitor completely charged, and after it is completely charged, that's okay, we will not have any current. So after it is completely charged, the capacitor current will be 0. But till a point where it charges completely, we will have some non-zero current, right? So it is nothing but the energy. So the energy for the capacitor to charge, so the energy that is consumed or stored in the capacitor for it to be completely charged to VDD, right? So in that sense, this definition is t is equal to 0 to infinite and not equal to t. So that will not be there. It will be nothing but infinite because this t value we really don't know. So in that case, for the capacitor to completely charge or store the energy, it will be nothing but Vc of t multiplied by Ic of t, where Vc of t is nothing but the instantaneous voltage across the capacitor, which is nothing but the output voltage, and Ic of t is nothing but the instantaneous current that will be flowing across the capacitor. Right, so this will be it. And if I consider Ic of t of the capacitor, the current flowing along the capacitor will be nothing but can be written in the form of C dVc by dt, right? So I will have this dt and dt get cancelled. So now I will have a new integral variable, which is nothing but dvc of t. So for t is equal to 0, I know that the Vc is actually 0. So we can assume that the capacitor is not at all charged. And then based on the once it is 1 to 0, the step input is given. When the PMOS transistor turns on, then only the capacitor starts charging, right? So when it is 1, when the input is 1, we know that the output will be completely, discharged to 0, and it will be holding a logic 0 in a steady state. In the moment the input does a transition from 1 to 0, we will have the PMOS transistor to be on, and then we will have the capacitor to be charging through the PMOS transistor. Right. So in that sense, we have the Vc is equal to 0 when t is equal to 0, and when t is equal to infinite, we know that the Vc will be held at a steady state voltage of VDD. Right. So if I take that particular limits, and now I have the variables here, Vc of t and then C dVc by dt. So this C is a constant, so I can take it out, and then Vc of t and then dVc of t. So it will be nothing but Vc square of t divided by 2. Limits will be 0 to VDD. So if I put that, I will get 1 by 2 C VDD square is the energy that is being stored or taken by the capacitor. Right. So this particular energy is now stored in the capacitor while it is completely charged. Right. So very interesting to find out that what is actually the energy that will be delivered by the VDD. Right. That will be delivered by this VDD rail. Now that is very interesting because the capacitor, although it charges to VDD, the energy that it stores or it is consumes will be nothing but half C VDD square. And the energy delivered by the VDD will again, as a component of this particular power source or the rail here, I can use the same definition, VDD of t, the voltage across that VDD rail with respect to the ground rail. Alright, with respect to the ground rail will be nothing but VDD of t. And then IDD of t, so this is the current that will be delivered by the VDD rail, and dt, and then of course time will be 0 to infinite. And VDD of t is nothing but, VDD is a constant value, it's a constant rail, it doesn't change with respect to time. So it will be nothing but, with respect to time it will be constant, so I'm just writing it as a constant value of VDD. IDD of t is nothing but IC of t, nothing but the current that will be flowing across the capacitor, and it is a time varying value. So in that sense, it will be C into dVc of t by dt. So this is the current that will be flowing across the capacitor. So I can rewrite this in the form of C dV by dt, and this is the dt. So this dt and this dt gets cancelled. So I'll be left with dVc of t. So what we are trying to find here is what is the energy that is being delivered by the VDD for the capacitor to completely charge to VDD, right? From 0 to VDD, what is the amount of energy that is being delivered by VDD? So that's why my limits will be 0 to VDD for my DVC here. So the capacitor voltage starting from 0 to VDD. So I will have this C and VDD outside. I will have only one, the integral here, variable here inside the integral, and that will be nothing but VC. The limits will be 0 to VDD, so I will get C VDD square. Right, so it is very interesting. The energy consumed by the capacitor is half C VDD square, whereas the energy delivered by the VDD is C VDD square. So the other half of, the other half C VDD square is consumed in some other component, is either released by some other component, right? Because the energy released by the delivered by the VDD is C VDD square. The energy consumed here or stored by the capacitor is half C VDD square. So the other half is actually spent by this particular PMOS transistor, which is always on when the capacitor is actually charging. So this PMOS transistor is going to use this half CVDD square because it has the voltage across it as the current flows through it, and hence it dissipates the half CVDD square continuously. So E of PMOS, so the energy dissipated by the PMOS is half CVDD square. The energy dissipated by PMOS depends on the capacitor. Of course, the capacitive load here, whatever is the capacitor size, whether it is 20 femtofarads or 20 nanofarads or picofarads. Based on that, it will dissipate this amount of energy. Because based on this capacitor, right, I will have this energy component, or rather I will have this current component which will be helping in charging this particular capacitor. So the energy dissipated by the PMOS depends on the capacitor, right? Depends on this particular capacitor load capacitance value, and not on the size of the transistor or the speed of the switching. Kind of very, very important to understand while in a digital circuit, while I'm pushing it to 0 to 1 or 1 to 0 here, the output actually switches from 1 to 0 or 0 to 1, and in 0 to 1, while the capacitor is actually charging, so it actually switches, the output node voltage actually switches. But assuming that it switches and it has sufficient time to reach the steady state, so the energy released by this PMOS will be nothing but half of C VDD square, which is actually equal to that of whatever is the energy stored by this particular load capacitance. Right, and then whatever is that energy doesn't really depend on whatever is the width of the PMOS transistor or whatever is the width of the NMOS transistor. All right, so hope this is clear. So let's take a look at the energy profile and then the power profile with respect to the time domain. So what we are really looking into is identifying what is the power in a transient analysis and what is the energy in a transient analysis. Right. So what we had looked into is, based on the input values, if the input was a step voltage, right, how did the output behave? So the output, while it was down, we said that it will be increasing, and then while the input was high, we said that the output will be decreasing. So this is my output profile, right? So, and this based on the input, we said what is the transient response of the inverter circuit. What we really want to do now is identify the output, not only the output profile, but also the current profile, so that the current and output profile will help us in giving us the power profile with respect to time. So we want to find out or estimate or derive a profile for identifying the instantaneous power with respect to time domain. And finally, we need to integrate it and then achieve the energy for the time domain. Right, and then come across with the average energy, or rather the average power. Right, so if suppose that is the case, what we want to see, so we have an inverter circuit and then the input is given, and let's say that we will start with a step input. So a step input of 0 to 1 or 1 to 0 is given, so that the other transistor is completely off and the only one transistor out of this PMOS and NMOS will be on. And the output voltage, the capacitive load here will either charge or discharge. So there is no contention there. I have just stated here, just to reiterate that if the output voltage is greater than VDD minus VT, if the output voltage is greater than VDD minus VT, we will have the NMOS transistor. So let's say that when the output voltage is discharging to ground, so that means that the input voltage is actually 0 to 1, a step is applied. So the NMOS transistor will be on, the PMOS will be off. So in that case, the output voltage, which it starts from VDD till it reaches VDD minus VT, it will be in saturation. The NMOS transistor will be in saturation. So the saturation current will be used, and that will be equated to the discharging profile, the discharging current equation for the capacitor. So minus C dV out by dt will be nothing but beta by 2 VDD minus VT the whole square. This is the NMOS transistor current. And from there, I should be able to find out what should be the output profile. The current profile is nothing but a constant, because beta by 2 VDD minus VT the whole square. When the output goes below VDD minus VT, I will have the linear region. So the NMOS transistor will be in linear region. And in the linear region, the current value is nothing but beta into VDD minus VT minus of V out by 2 and then V out. So I will have an exponentially decreasing profile. Here, the output profile, when the NMOS transistor in saturation, the output profile will be a linearly decreasing profile. Right. So this is something we had already seen, and we will use this so that we will get the output profile. We'll also draw the current profile, and then finally draw the power profile with respect to the instantaneous power profile with respect to the time domain. Right. So this is what we have. So I have an input voltage. So it is 0, and then it is the input voltage goes to 1. So whenever it is 0, the output voltage will be 1, steady state voltage, and then when it does the transition from 0 to 1, I'll get the output voltage doing the transition from 1 to 0. And then while it is doing the transition from 1 to 0 back, the output voltage will do the transition from 0 to 1, and then so on. All right. So this is the output profile, the current profile. And the current profile I have anyways drawn. Just to understand the output voltage profile, so let's take a closer look into it. This is a linear profile, all right? So it is a decreasing profile. So whenever the step voltage, the input voltage is high, we know that the NMOS will be on, right? In fact, in both the decreasing profile, the NMOS will be on, the PMOS will be off. Here, the PMOS will be on. And that's why we will have the output node voltage charging the capacitor through the PMOS transistor. Here the capacitive load or the output voltage decreases through the NMOS transistor. This particular region I have drawn it linear because I am getting the NMOS to be in saturation. I will have a constant current, and therefore the output voltage will be a linearly decreasing profile. So I'm going to say that it is a NMOS in saturation. And this one I will say that NMOS is in linear region or triode region. Similarly, here in this particular case, PMOS will be in linear region, or rather in saturation region. So that's why I have a linearly increasing profile. The output voltage is linearly increasing, and then this particular region is PMOS will be in linear region, and that's why we will have an exponential profile. Right, exponentially increasing profile. Here, when the NMOS is in linear region, we will have an exponentially decreasing profile. So this is my output profile. So I'm going to write it as output of T. Right. So hope this is clear. Let's take a look at the current that is flowing across the capacitor. During the linearly decreasing profile here for a step input of, while it is doing the transition from 0 to 1, and then when it is held 1, so we will get the NMOS to be in saturation. So that means that the NMOS current is constant. So that's why I will have a constant value here. Post that, while it is actually the output voltage is decreasing, all right, exponentially decreasing, we should have an exponentially decreasing current here, right, of the NMOS current. Right, the reason is very, very simple, because the output voltage is actually going down. So my VDS value for the NMOS is going down, and that will have an effect on the current, and it will completely decrease. And if I want to find out the PMOS current, the IDS of the PMOS current, again, during the output voltage being linear here, the PMOS current is in saturation, it will be constant. And while it is exponentially increasing, the output voltage is exponentially increasing. That means that the VSD value for the PMOS is decreasing, and thereby the current will be decreasing and then eventually reaches 0. So this particular current profile, I have drawn it as the IDS of NMOS and IDS of PMOS. right? But if I want to consider the capacitor current, right, and if I really want to do the this particular current as nothing but the charging current, so the current direction is nothing but, so if I consider this as an inverter and this as my capacitive load, right, let's say that this is my current direction of the capacitor. So if this is my current direction of the capacitor, IC of t, right, this is in alignment with that of the ISD of the PMOS, right? So this should be nothing but ISD of the PMOS. All right, so this is in alignment. So my IDS of the NMOS, right, so while the capacitor is discharging, will be exactly opposite. So what I've done is, although I've drawn the profile of IDS of NMOS, so this profile for the capacitor current direction, I will have it negative. So the discharging profile will be negative, the charging profile will be positive for the capacitor current. So I will have the negative profile of the current and then the positive profile while it is charging and negative profile while it is discharging. So now I have this particular current direction and then this particular current direction. And now I want to have a product of this output voltage and then, which is nothing but the capacitor voltage and then the capacitor current, so that I'll get the power consumed or stored by the capacitor, the power consumed by the capacitor. So if I do the multiplication of this profile and then with that of this particular negative profile, I'll get this particular profile, right? A constant is there. So constant with multiplied by a linearly decreasing profile will be a linearly decreasing profile. And then I will have this particular decreasing exponential profile multiplied by exponentially decreasing profile. I'll get a faster rate in decreasing profile, often it will be close to an exponential profile. And for charging of the capacitor, while the capacitor is actually consuming the power, so this is the power while it is actually dissipating, while it is discharging, and this particular power of the capacitor while it is charging. So it is actually consuming the power, it is actually using that power to store the energy. So in this particular case, it is linear here and it is constant, so I will have a linear profile here up till this particular point. And after that, I will have an exponentially increasing profile and then exponentially decreasing profile. So what it will do is the multiplication of this particular profile and this particular profile, I will have a slight increase and after that it is going to decrease. Right. So note that if the PMOS, if the PMOS is helping in charging the capacitor and then the NMOS is helping in discharging the capacitor. So the energy or the power here, whatever the profile here I've got, right, the area under this particular profile, right, the area under this particular profile of the power should match with that of the area under this particular profile of the capacitor while it is discharging, right? So this particular power area and then this particular power area in the sense, in this particular power, whatever is that area I calculate, and then this particular area, whatever I calculate in this particular profile should match. And the reason is very simple. The capacitor actually charges, charges through the PMOS transistor and then it discharges through the NMOS transistor, right? So the area under this particular power curve or the power profile will give me the energy term, right? And then the area under this particular profile is nothing but the energy term, right? So the capacitor can actually store the energy and the same amount of energy is actually released, right? So the capacitor stores the energy through the PMOS transistor and it discharges the whole amount of energy through the NMOS transistors. Right. And what I've done is, in this particular step input, I have once again given a step, 0 to 1 here. So it behaves very, very similarly to what we had seen in this particular time domain. So it decreases and then, we will have the same profile of the current. And so I will have the same profile of the power here also. Right. So I started with the step input of 0 to 1 and then 1 to 0 and then 0 to 1. So I have 3 such profiles for the output voltage, for the currents, for the power. So from now on, what we will do is we will consider the charging first and then the discharging, right? So we are going to ignore this effect. So what we'll do is we'll start with this particular profile, charging, and then of course the discharging. So the input side, it will do a transition of 1 to 0, right? And then that will help in charging the output node, charging the capacitor, and then from 0 to 1 it will start discharging. So I will start from here. My time domain, or rather in the next figure you will not see this particular figure at all. So you will see the power with respect to time domain, the instantaneous power in the capacitor starting from this particular axis or this particular time domain.